So we've heard about the CPU this morning. We've heard about the network before the break. The last ingredient is to hear about the GPUs. And so this is on the program as an introduction to OpenACC, which is a way of programming GPUs, but you don't really program a GPU. The GPU never kind of lives on its own. The GPU is an accelerator that's attached to the CPU. The CPU is always involved to some extent. And really, you would like to be using the CPU and the GPU to be involved in the computation. And I mean, that's another step of complexity. But either way, the CPU is always involved. So really, it's an introduction to hybrid programming rather than GPU programming. But I've also included, I mean, originally this was just going to be about OpenACC, but it would seem strange to not mention CUDA at all, since this is, the dominant programming model for the Nvidia GPU. So I've added a few slides introducing a little bit about CUDA. So this is by no means a complete introduction to CUDA, and it'll be very short and sketchy, just because we only left limited time. The bulk of it will be about OpenACC, but even with the OpenACC, this isn't a complete course on OpenACC programming. I'm going to talk a little bit about basic concepts, and those are generally applicable to CUDA as well as to OpenACC. You're programming the same device. But, we give whole training courses on OpenACC, and if you want to find the slides and lectures for one of those, then there's a link in the PDF to one that was given at CSCS, so that you can go and find all the videos on YouTube, and you can spend, I don't know, there's 10 hours worth or something, so you need never worry about what's on TV. So it's a little bit about the basic directives and how you would use them to port the code. I mean, I'm not going to talk anything about performance optimization, and on the one hand, that is, that's why we have a big course, is it's a big topic. On the other hand, that's really a second step. The key to getting good performance out of GPUs is not about thrashing the instruction set of the GPU. The real key to getting good performance out of the GPU is minimizing the use of the PCI Express bus that connects the CPU to the GPU. And you will spend most of your time doing that. Now, in the practical that comes after this, which is going to be this Himeno code again, it's a step-by-step acceleration of the code. And I kind of apologize slightly that if you would, if you go to a big course like this one, there's whole lectures kind of explaining the process of how to do it. Whereas you're being left a little bit more to your own devices to see what the changes are in the code based on what you hear in this one lecture. But if you run this code, it goes step by step in 4 stages, accelerating the code with OpenACC. And what you see is the big performance boost comes from, not from executing loop nests on the GPU instead of the CPU. It comes from keeping the data on the GPU and not using the PCI Express bus. Beyond that, there is some tuning you can do in the kernels, in the GPU code, and you can get extra performance. You might get a factor of 2 or so speed up. But compared to the factor of 20 to 25 times speed up you got by keeping the data on the GPU and not using the PCI Express bus more than you needed to, the main optimization is keeping the data on the GPU. And you will hear basically everything you need to know about that in this one lecture. How fast are GPUs? What should you expect? So this is a picture of one of the little daughter cards that's in Daint. You've got 2 CPUs. They've got memory associated with them. You've got 2 GPUs. Each one of these is a node. The CPU, we've heard already, gives you about 170 gigaflops. It's got 32 gig of memory. You've got about 50 gigabytes a second of memory bandwidth. The GPU gives you about 1.3 teraflops peak double precision. You probably won't ever reach the peak, but that's what it gives you. It's got less memory. It's got 6 gigabytes, but the memory bandwidth is better. So if you look at the ratio of flops, you've got to say a factor of 8. If you look at the ratio of memory bandwidth, you've got a factor of 5. So in all honesty, if you use your CPU properly, so you use all the cores on the CPU, and you compare that to using the GPU, you should see a speed up of between 5 and 8 at the very most, because those are the bandwidth and the flops limited factors. You probably won't see that. In general, if you see a factor of between 2 and 3, you've done well. But that's still, a factor of 2 or 3 is pretty good. But the thing that limits you is this slow link between the CPU and the GPU. In order to get the peak performance, you've got to minimize the data transfer backwards and forwards. And also, because we've seen the CPU is engineered in a way that, this is a slide stolen from Nvidia, but if you look as a sort of block diagram at the silicon of the CPU, you've got a big load of cache, you've got a big load of control, and that control is all this out-of-order execution, optimizing how, if you like, badly written code can be made to execute much better on the CPU. And the small amount of the die is actually the floating point calculations, the arithmetic logic units. If you go across and look at the GPU, you've got a small cache. You've got hundreds of these arithmetic logic units, thousands even. But the control element of this is really small. The GPU does what you tell it to do, and if you don't tell it to do it in a way that fits its architecture, you will get bad performance. With a CPU, it can do a lot so that you can get reasonable performance even with a badly written code. On the GPU, you have to tailor your code to the GPU. If you don't do that, you'll get bad performance. And that doesn't matter whether you use CUDA, you use OpenACC, you use OpenCL, you use any programming model. There just isn't the silicon to work around what you do. Now, execution and memory models. I mean, if you're not a computer scientist, and I'm not, my eyes glaze over when people start talking about these things. But it is kind of important, but it's probably something you already understand, even if you don't understand it in exactly these terms. The CPU is essential. The CPU is in charge. Everything happens from the CPU. So the main program starts on the CPU. Again, CUDA, OpenAC, whatever. It can offload tasks to the device, as it's called, the GPU. These could be computational tasks, they could be data transfer tasks. But it's the CPU that does this. The CPU does all the managing, not only of its own memory, but also of the GPU memory. And it also does all the synchronization to check that the GPU is finished doing the tasks that were sent to it. The CPU and GPU have separate memory spaces. There is no automatic data synchronization going on. There's no cache flushing that keeps the data synchronized between them. The GPU memory is fragmented. We heard a little bit about how the GPU is split up into these SMXs, which are like independent vector processors, and they really are independent. There is some memory that's shared between them, but the only memory that's global is the global memory. And this leaves a big potential for race conditions, where each time you run the code, you get a different answer because things happen to execute in a different order. So if you don't take account and make sure that can't happen, you can get wrong answers. Now, the difference between, all of this is true whether you're using OpenACC or CUDA, because it's the hardware, it's just the architecture. The selling point of OpenAC over CUDA is, I would say, that the compiler and the runtime have much more scope for helping you if you're programming in something like, in a higher level way. With CUDA, you're very much in charge. If you know what you're doing, you can get great performance. But if you don't know what you're doing, or you get it wrong, or you just don't do the right thing, you can get terrible performance. So how does a program execute? The main program runs on the CPU. Some of the code will run there. It might be serial code, it might be parallel code with OpenMP, but some of your code is running on the CPU. This could be because the code should run there, you just want it to run there, either because it's very hard to port that bit of the code to the GPU, or because there isn't enough work to justify using the GPU. Some of the stuff is control statements, managing GPU memory, synchronization, that has to execute on the CPU. Some of it is things like calling the MPI library. You can't call the MPI library from the GPU. it's done from the CPU, even if you're telling it to process data that's on the GPU. So the main program then launches these tasks, these computational tasks to the device. These computational tasks are called kernels. They have to be written specially for the GPU. So you either have to use some sort of new programming model like CUDA, or you have to use some extension to an existing programming model like OpenACC. GPU kernels are executed by many threads in parallel. It's a very parallel way of doing things. All the threads are executing the same code. They're doing the same operations, but they're doing it on different data. So that's how you get, obviously, the different process, all the elements of an array, but you have to process them in the same way. The threads can take different paths through the code. If you have an if statement, then you can have, if this is true, do this, otherwise do that. But what you actually will end up doing in most cases is you'll end up with both sets of tasks. But in one case, half the threads, or whatever the right proportion is, are idle and waiting. And then for the else branch, the other half are just idle and waiting. But this isn't always true. And I mean, this all comes down to things like warps that I'll talk about in a minute. Each thread has access to a unique ID, especially if you're writing in CUDA. And this is how you make the decisions about which data element to process and how to make these decisions. When your thread executes on an Nvidia GPU, you have all these threads to execute. It's not like OpenMP, where basically you just have all these threads to execute. The threads are actually grouped up into blocks, a logical grouping. And typically, there are a few hundred threads in a block. And then all of the blocks, to make you've got multiple blocks that make up all of your thread team, and this is called a grid of blocks of threads. Within that, your thread has a coordinate. That's its ID. Now, you can either have just a simple number your threads from 0 to whatever it is, 1023. So they just have they basically, if you think about X and Y and Z, they just have an X coordinate. It's just a one long line. But sometimes it's convenient to make this ID, instead of just an X coordinate, it could be X and Y, or it could be X and Y and Z. And if you're processing a 2D array or a 3D array, there's some logic to doing it in that way. This doesn't affect anything. This is simply how this coordinate, how this unique ID is constructed. So that's how you program it. You write that lots of threads are going to do this. How do the threads execute? Well, each block of threads, the reason that we group them into blocks, which from a programming perspective didn't really make a lot of sense when I talked about it, the reason you do it is that the threads within a single thread block will be assigned to one of these 14 symmetric multiprocessors, these SMXs. Because when I showed you that block diagram of the GPU, you had all of these cores, but they were divided into 14 SMXs, which were like independent vector processors. Each thread block will be sent to a single SMX where it will be executed. It won't move anywhere else. You can have more threads than there are cores in an SMX, and it will just, it'll just work its way through them. It'll do them in chunks until it's done on the cores in an SMX, it has executed all the threads. You really want this to happen because you want the GPU to have enough computational work. So simply because there are however many cores there are in an SMX, and I forget the exact number, but there's 64 or 128. That doesn't mean that you only want 64 threads. You want a lot more than that in your thread block. The entire grid of threads has been split into multiple thread blocks, and different thread blocks will execute on different SMXs. You've no control of which one it goes to, they just do. Several thread blocks could well be executing on the same SMX. They'll be swapped in and out of execution. You really want this to happen as well, because they're swapped in and out of execution to hide memory latency. if the first thread block is waiting for data from memory, it'll start executing the second thread block, and then it'll come back and start and resume the first thread block when the data arrives. The more thread blocks you've got, the more you can hide the memory latency. You have no control over this. You cannot predict which order they execute in. There's no way to kind of make a barrier on the execution of these different thread blocks on different SMXs. So this is a kind of the non-reproducible part of a GPU execution. But you do want this to be happening because you need to be able to hide memory latency. So there's no interaction between the different thread blocks. You can have interaction within one thread block that's on a single SMX. And they can interact by communicating data, and you can synchronize at that level. You can't have a global barrier, but you can have a barrier within a thread block. So CUDA is the programming model that Nvidia supply for programming the GPU. And all of these concepts are very obvious in the programming model. So the programming model is very mapped onto the hardware and how it's going to execute. And it's all made very obvious. It's basically C++ with extensions. PGI do a CUDA Fortran, which is an extension to Fortran that provides the same functionality. So basically, this is a slide. This text is from an Nvidia slide. So, it's wonderful. It scales. It lets you focus on the parallel algorithms and these sorts of things. It can give you very low-level control of the GPU. So in CUDA, you can put in inline GPU assembly instructions. You can do all sorts of very low-level things. So you can get really good performance if you really understand the architecture. But the programmer has to do a lot of things because everything is relatively low-level. The compiler is not doing a great deal for you. Now, the programming philosophy of CUDA is very different to most of the languages you might be using on the CPU. In Fortran or C, you take a top-down view. Here is my array, and I will now write a loop nest that will process all of the elements of the array. So you have a kind of view of the whole array, put the loop nests in, and then you put, say, OpenMP in, and you still have the whole array, but you just say, split this workup between the threads. But you're still looking at the whole array as you write your code. In CUDA, it's a very bottom-up view of things, in that you don't write from the perspective of the whole array. You write from the perspective of a single thread. And you say, this thread is going to do this operation. It's going to do a finite difference. It's going to, for a particular array element, it will do the finite difference of one element to the right and one element to the left, for instance, if this was a simple stencil. And you write it from the perspective of that thread. The compiler then glues that together for all the threads in a thread block and for all the blocks in a grid, and works out, where the threads can cooperate to load data from memory in the most efficient manner and all these sorts of things. But you write it in a different way. It's as if you are a thread as opposed to you are the whole MPI rank, which sees the whole array. So here is a CUDA example. It's a very simple example. Basically, it's going to double the values of an array. And, it's quite frightening to put it all up there, but that's what it looks like. So I was going to talk you through it, not to teach you CUDA particularly, but to show you the sorts of things that you do when writing CUDA. So you have a main program, and you're going to have an array on the CPU. You should initialize it. I didn't initialize it because there isn't space on the slide. And basically what you're going to do is you're going to send that array to the GPU and double the values, and then bring the array back. Is that a sensible thing to do? No, of course it isn't. You shouldn't be sending an array to the GPU merely to double the values, because the data transfer costs will kill you. But it's a simple example, so ignore the performance, just the functionality. So what do? The first thing you must do is you must provide space in GPU memory for the array. So I have a pointer, And this pointer, I use a CUDA command called CUDA malloc, which will allocate space in GPU memory and return the address for me. When I've done that, I would like to copy the values from the CPU to the GPU. So I use a command called CUDA memcopy, and I have to tell it in which direction to move the data and how much data to move and where it is in CPU memory and where it should go in GPU memory. And I must get these the right way round. And I never remember which way round it should be, but you have to get these the right way round. Then I would like to actually double the value. So what I would like to do is I would like to execute some code on the GPU that will double the values. So I do this by doing a function call, but it's a sort of strange function call with these extra arguments. When I do this, I will launch this work off to the GPU, and the GPU will immediately return control back to the CPU. It doesn't mean it's finished doing the job. It just means that it started doing the job. This will execute so quickly that maybe they're the same thing, but if this was a big meaty kernel, that isn't the case. To make sure that it's actually finished, I have to do a host-side synchronization. So I have to use a special call. I said there's no global way to synchronize a GPU, and I mean from within the GPU. Once you are back on the host, you can do a whole synchronization across the GPU. But I can't do it midway through a GPU computation. So here, I know now that it's finished. Now I should bring the data back. So I do a CUDA memcopy, but in the opposite direction. And I have to remember to put these the right way around, and that's how much data must come back. I can then free up the space on the GPU, and I'm finished. So the actual thing up here, I have to write a special function with a special qualifier, global, which tells me that this is going to be something that executes on the GPU. It's going to accept in a pointer in GPU memory. It's going to double the values of this. How do I know which element of the array to double? I have to use the unique thread ID to construct which element of the array to process. And in this case, what I do is I take the single X dimension, because I'm not going to use a multi-dimensional thread block, I'm just going to use a single one. It's a single-dimensional array, why not? I use this very common pattern that you will see, slightly unintuitive, but that's what I do, to give me a value of I. If I is less than the size of the array, double the values. Why do I need to do this little check? Well, that's because if my array is a sort of strange size, because of the way that I have to break up my threads into thread blocks, all my thread blocks are the same size. So the last one, so they might be, if my array is size 100,